Good morning, grade 12s. Welcome to Wednesday, June the 3rd. We are rapidly approaching the end of our course. As we get started today, I do want to share with you a verse of the day before we get going. So today's verses of the day come from 1 Corinthians 15. I'm going to read for you verses 40 and 41, where it says, "There are also heavenly bodies, and there are earthly bodies. But the splendor of the heavenly bodies is of one kind, and the splendor of the earthly bodies is another. The sun has one kind of splendor, the moon another, and the stars another. And stars differ from stars in splendor." And so there you go. Again, another verse talking about the glory of God and the splendor of His works that we see in the skies above us. Today we want to continue our discussion on planetary mechanics by looking at Isaac Newton and Isaac Newton's law of universal gravity. And so it was in the late 1600s, 1684, 1687, in those years, it is where Newton worked and did his experimenting that came up with his three laws of motion as well as this law of universal gravity. And it was in 1867 that he published his famous book called Principia, which is where he published the work that showed his three or four laws in this case. And what he showed was that gravity was a universal force, not just a force that we experienced here on Earth, but it was a force that was experienced throughout the universe. And of course, he had to work out a lot of math that worked with it. And again, it worked with elliptical orbits. So again, this was a case of him going against the commonalities of circular orbits for the planets and other things. And his universal law of gravity works with elliptical paths for the planets. And so the law is any two bodies attract each other with forces proportional to the mass of each object and inversely proportional to the square of the distance between them. Now it's important to note that it does say any two bodies with a mass, and that includes any two bodies with a mass. We are going to be looking at planets and stars and massive objects with very large masses, but this does also work with smaller masses like two people or like a basketball and a volleyball or whatever it might be. But because those masses are so small, the force is extremely small and unquantifiable for the most part. So when we put this together, we get this proportionality statement. We get the force is directly proportional to the mass. So as mass increases, force increases by the same amount. So if we double the mass of one object, we'll double the force. If we double the mass of both objects, then we will have 4 times the force. All right, so it's directly proportional to mass. It is inversely proportional to the distance between the two objects squared. All right, so if we double the distance between them, we're going to end up with 1/4 of the force. All right, because it's the squared part of that. All right, now, when we want to change a proportion to an equation, we need a constant. And so what happens is to change this to an equation, we get F equals, now we get a capital G, M1, M2 divided by D squared. And this capital G is our gravitational constant. It's Newton's gravitational constant. And I'm going to give you the number momentarily for it, but I do want to point out something too. When we're talking about planets and stars in our solar system or in the universe, when we have this formula with the d squared in it, it could also be an r squared, okay? Because we're looking at the distance between the two objects, but in space, objects rotate around one another. And so as it rotates around, it's going to map out a circle. It'll be an ellipse most likely, but for all intents and purposes, they're close to a circle and close enough to a circle. And we always use the mean distance between the two, the average distance, so it balances that out. But it maps out a circle, in which case R stands for radius. Okay, so they are interchangeable. You will see the formula sometimes with D in it for the distance between the two objects. You will sometimes see the formula with R in it, which is still the distance between the two objects, but now the objects are rotating around one another. All right, now what does G equal? G equals the following number. Okay, so capital G, gravitational constant, is 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. All right, so again, it's that negative 11 factor that keeps us, when we have small masses, we're going to get a really, really, really small force. When we have large masses, like the mass of the planets or the mass of the sun or other stars, then we get forces that are fairly large as well. All right, so this is our proportionality statement. This is our equation. This is our constant. You do not need to memorize the constant. If you need it on tests or assignments, you'll get it. But let's do an example of how we're going to use this, and then you will get an assignment. Here's our first example. It says, what is the gravitational attraction between two basketballs, each with a mass of 0.65 kilograms that are 1 meter apart? And so we're going to start with our formula, F equals G, M1, M2 over D squared. We're going to fill in our numbers. Of course, G is 6.67 times 10 to the negative 11. Our masses, M1 and M2, are both 0.65 kilograms. So rather than writing it twice, I simply squared the number, and it's divided by 1 squared, giving us a value of 2.8 times 10 to the negative 11 newtons. All right, and again, because this is a very small number, times 10 to the negative 11, it's not something that we would ever experience or feel, because it's literally 0.000, a bunch of zeros, 2, 8, and yeah, too small to quantify, too small to experience, and so that's why we would never see two basketballs randomly just attracted to one another with a gravitational force. All right, so we're going to leave it at that today. You will get some questions that require you to use the proportionality statement. So just read those questions carefully and remember that it's directly proportional to the mass and inversely proportional to the distance squared. All right, so like I said earlier, if you double the distance, you are going to 1/4 the force. Okay, so keep that in mind as you do these questions. You're going to, again, get a handout on Connect, and I think it's 4 or 5 questions that you'll do. Ask any questions that you have. If you haven't already done it, answer the poll question that is on the Planetary Mechanics page, and we will see you tomorrow. Have a great day.